This video will teach you how to identify when a chemical change has occurred and also how to balance chemical equations. So there are some visual clues that a chemical change has occurred. Just because one of these visual changes has occurred doesn't mean a chemical change necessarily occurred, but it is quite possible it did. One example of a chemical change is if you see a color change. So when you see leaves changing color in fall, it's because the green chlorophyll in leaves starts to decompose and break down into smaller chemicals. And that exposes some of the other colors that are in the leaves. So that is a chemical change occurring because the chlorophyll is no longer chlorophyll. Another thing that might indicate a chemical change has occurred is emission of light. Now, emission of light doesn't always mean that you have a chemical change occurring. We learned in chapter 2 that if you excite electrons in a substance, then that energy can be released as light. But in other cases, emission of light is caused by a chemical reaction, giving those electrons enough energy to jump up into higher energy levels. And then when the electrons fall back down, they do emit light. But it's the chemical reaction that's occurring that gives the electrons enough energy, not an external source. Also, emission and absorption of heat is another clue that a chemical change has occurred. When we did our calorimetry lab earlier in the semester, you observed some temperature changes when we dissolved stuff in solution and when we did some chemical reactions in solution. Another sign that a chemical change has occurred is the formation of a gas. For instance, we talked about how baking soda decomposes when heated and releases carbon dioxide gas. And so that means it's no longer baking soda, it's now carbon dioxide gas and some other byproducts. Also, formation of a solid that was not there before is another example of a chemical change occurring. And so I have a picture of a rusty pipe, and that's a different solid than what was on there originally. And so some kind of chemical change has occurred there. But just because you observe one of these phenomena doesn't mean that it was necessarily a chemical change. Some physical changes also release light or release a gas, for instance. So phase changes, we have to remember, are physical changes. And by a physical change, we mean the identity of the chemical species does not change. Only the state of matter changes. And so if only the state of matter changes, then it's a physical change. But if we had something like H2O breaking apart into hydrogen gas and oxygen gas, since we no longer have water in the end, that is a chemical change because we don't have the same things on both sides of the reaction arrow. So since water liquid turning into water gas is a physical change, the only difference here is that we're breaking the intermolecular forces. We're not breaking covalent bonds. We're not breaking what holds the molecule together when we're doing a physical change. So we have some methods for communicating reactions. Now we can also communicate physical changes through equations too, but we'll be focusing primarily on communicating chemical changes through chemical equations. So what a chemical equation is, it's a way of expressing what did you start with and what did you end with? What change occurred? And so the only things that should appear in here are things that changed. So for example, on the left side of the equation, we always have the reactants. And so on the left side, you always have what you started with. You have an arrow to separate. That says separate. And then on the right side is where you have your products. Now, it doesn't matter what order you have your reactants in. And so I listed sodium hydrogen carbonate first, but I could have listed water first. It wouldn't make a difference. As long as they're on the same side of the reaction arrow, then it doesn't matter. So like I could swap them, that's okay. Or I could leave it as is. It does not matter. Either one is okay. As long as it's all there, that's the only thing that makes a difference. Okay. So, and then you can see we also have our states of matter represented here. And so we have solid, liquid, or gas indicated. So we have solid, liquid, gas. I need to get my pen working again. So the phase symbols represent what state of matter it is. And so you can see that we have water on both sides of the reaction arrow, but it does change phase. And so that is a change that's occurring, and so it should be represented in the chemical equation. Sometimes when I'm talking, I might say the word reagent instead of reactant. Just pretend I said reactant. I can't fix myself. All right. So here's an example of a chemical equation about methane gas burning. So methane gas is the gas that's from your stove. And so that's like natural gas, also known as natural gas. So that's methane. And it burns an oxygen gas to produce carbon dioxide and water. And so we will learn that all combustion reactions produce carbon dioxide and water. We'll do that in a few slides or in another video. I'm just going to write that out. All combustion reactions produce CO2 and H2O. That's as long as you're starting with something like a hydrocarbon that contains only carbon and hydrogen. So this is a hydrocarbon. It contains only carbon and hydrogen. And so the products are always carbon dioxide and water as we're burning. So how this equation is translated is methane is CH4. You wouldn't know that because you haven't taken organic nomenclature, but organic or oxygen gas is O2. Carbon dioxide, you do need to know your nomenclature. And so those ones you would have to know. But we can translate that into symbols. And so when we have this to produce, that means an arrow. So if we were going to write this out, we can see that we have a methane molecule and reacting with two oxygen atoms. That's a diatomic molecule. And it's going to produce carbon dioxide and water. But there's a slight problem with how this is written so far. Does anyone see the problem? Our atom counts aren't the same. If we look over here, we have 4 hydrogen atoms, and over here, we only have 2 hydrogen atoms. That's a problem because we can't create matter and we can't destroy matter. We also can't turn hydrogen into a different element. we have to maintain the same number of each atom on both sides of the equation. And so we have to edit our chemical equation a bit. And to do that, we need to add what's called stoichiometric coefficients. And so stoichiometric coefficients are numbers that are added in front of the chemical formulas in order to indicate how many of each compound or each element we have. And so a number like this, a 2 in front of O2, means that we have two different O2 molecules. And so you can see I have one here, and then I have a second one here. And so that's why I put a 2 coefficient in front of that O2. I can't write O4. That would be wrong because that would mean I have 4 oxygen atoms bonded together, and I don't. I only have O2 molecules. I just have 2 separate O2 molecules. So we don't have that. So we have to make sure we have our chemical formulas correct, and then we balance them. That's very important. And so once our equation is correctly balanced, we'll have the same number of each element on both sides of the equation. So I have a strategy here to help you figure out, well, most of balancing equations is trial and error, but you do need to get your product chemical formulas correct first before you even attempt to balance. So we have to think about like what are the common ion charges, which elements are diatomic, and we really have to make sure that we're getting our chemical formulas correct before we move forward. We're going to be learning patterns of chemical reactions in another video that will apply to help us predict products. But we still need to get our product chemical formulas correct. After we get those correct, then we can start getting our stoichiometric coefficients written in front. I would focus on balancing really complicated chemical formulas first, or things that appear in really complicated formulas, and save pure elements for the end. And then sometimes you might end up with a fraction, or it would be really convenient to end with a fraction, but we can't have like half of a molecule. And so you might need to multiply by a coefficient in order to clear fractions and end up with whole numbers of things. And then once you have your equation balanced, then you can go back through and apply your solubility rules in order to determine if things are solid, aqueous, or whatever. So we're going to be doing some word problems where you have to translate words into chemical symbols. And so I have some key words on this slide to help you translate words into chemical formulas. And so for instance, if you see something like it burns in air or it's combusted, that means it reacts with oxygen gas, which is O2. O2 is the most reactive gas in air. Also, if you see blah, blah, blah metal, like copper metal, gold metal, metals are solids. That's telling you the state of matter. Remember our poem about how on the periodic tables in the classroom, gases were red, liquids are blue, the rest are solids. That's all you need to know. Like the metals are solids. So when they're telling you it's a metal, it's a solid. Also, if they say acid, acids, we're going to be working with aqueous acids, and so it's another way of implying the state of matter without telling you the state of matter. Additionally, you need to know your diatomic elements. Your diatomic elements are, like, remember our acronym of have no fear of ice cold beer? That's the hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine exist as diatomic elements. So I'm going to do another example problem where I'm going to balance things. This one's going to have what we call interfering coefficients, which means I'm going to end up with a fraction and then I'm going to have to clear the fraction. That's a more complicated example. On ALEKS, you'll encounter both interfering coefficients and non-interfering coefficients. So the example problem reads, liquid hexane, which has a chemical formula of C6H14, is burned in oxygen gas to produce carbon dioxide and water vapor. And so we first have to translate our names into chemical symbols. And so the first thing that was listed was our hexane. And we were given the chemical formula of hexane, so that one was easy. The next thing that's said is oxygen gas. Oxygen is one of our diatomic elements. To produce is a arrow, a way of showing what the difference is between our reactants and our products. Then we have carbon dioxide. It does say gaseous carbon dioxide, but I'm not going to worry about my state symbols quite yet. And then water has a chemical formula of H2O. All right. So, in a combustion equation, I'm going to start balancing carbon and hydrogen, and then I'm going to save oxygen for last. Because oxygen exists as a pure element, and so I'm going to save that one for the end. So I'm going to write save pure element for the end. What I mean by that is let's balance the carbon and the hydrogen first, and then we'll go back and work on the oxygen. So sometimes when you're balancing or learning to balance, it's easy or to remember to like draw a line for where the coefficient should go. That helps you plan your space, and it also reminds you to put the number in front of the chemical formula instead of changing your subscripts. You might also find it nice to kind of have your reactants versus your products in a table, and then have your element counts. I see carbon, hydrogen, and oxygen. And so I see 6 carbons here on my reactant side, and I currently only have a 1 on my product side. But if I write a 6 there, then I won't have just 6, I will have 6 carbons. Now I have 6 carbons on both sides of the equation. On my reactant side, I have 14. On my product side, I have 2. So if I multiply my water by 7, then I will have 14. Next up, I have to figure out my oxygens. I have a lot of oxygens on my product side, and so I'm going to count up those first. I have 12 oxygens from my carbon dioxide because I have 6 times 2. And then I have to do 7 times 1. 7 times 1 is 7. And so on my product side right now, I have 19. On my reactant side, I have 2. And so I have to figure out what can I multiply by 2 in order to end up with 19. And so I'm trying to figure out what number I can multiply by 2 in order to end up with 19. And so if you were in algebra, they would say, oh, just divide both sides by 2. And then you're like, boom. What goes there is 19 halves. And so this is 19 halves. And so now 19 halves times 2 is 19. There's a lot of animations. But we can't have 19 halves. We had 19 halves of oxygen. And we're like, no, we need a whole number. So that means we have to multiply everything by 2. So if we do something to one coefficient, we have to do it to all the coefficients because we have to be balanced in the end. So if we multiply, I'm trying to rewrite my equation now that I'm on another page. So now that I'm on another page, if I multiply, let me change colors. So if I multiply that one by 2, then I have to multiply all of them by 2. And so that means I'm going to have an equation that is 2C6H14. And then 2 times 19 halves is 19. And then that is 12. And then 14 H2O. Now that I have my balanced chemical equation, I can go back and I can add state symbols. And so I was told that that was a liquid. I was told that that was oxygen gas. And I was told that that was carbon dioxide gas. And I was told that that was liquid H2O. And there we have it. So here's a practice problem for you. Go ahead and pause the video and try to work it out on your own. Okay, if you're listening to this, I hope you solved the problem and you're here to check your answers. Let's start by balancing the first one. If I'm looking at this, I have 4 phosphoruses and only 1 on the product side. And so I'm looking at this here, and I can see that I have 1 phosphorus and 3 bromines. And so the bromines are going to conflict a lot, but I'm also concerned about my phosphoruses. I'm going to multiply this by 4 in order to balance out my phosphoruses. And so if you want, you can have your little table with phosphorus versus bromine. And that's 4 now, and that's 4. But that 4 also changes our bromine count to 12. And so in order to have 12 on the reactant side, I have to have a 6 there because 6 times 2 is 12. All right. Next up, we have to I'm going to erase that. Okay. We have to balance this one. Okay, so for our second one, I can see that we have these 2 chemical formulas that have a lot of subscripts happening, but both of them contain 3 oxygen. So at least if I keep their coefficients the same, then my oxygen will stay balanced. I can see that I have 2 aluminums here, so I can put a 2 there, and I have 2 irons there, and so I can put a 2 there, and that would balance out my irons versus my oxygen. And so I should have, yep, that's balanced. All right, next up we have this equation. This one has a polyatomic ion. PO4 is a polyatomic ion, and notice how it stays as PO4 on this side. That means we don't have to think of our polyatomic ion as separate phosphoruses versus oxygens. We can think of it as a whole. It behaves as one ion. So on the products side, I have 2 phosphate ions. On the reactant side, I have 1 phosphate ion. So if I multiplied that by 2, I would have 2 phosphate ions on both sides of the equation. But that 2 changes the sodiums, changes my counts of sodiums as well to 6. And so I have now 6 sodiums. On the product side, I only have 1 sodium. So if I multiply that by 6, I will have 6 sodiums. That 6 also changed my chlorine count. And so I have 6 chlorines. So I come over here and I can put a 3 there. That 3 also applies to magnesium, so I have 3 magnesiums. And in this chemical formula on the product side, I also have 3 magnesiums. So we're all good. For our last one, it says aluminum metal, and so that is Al, and so it's saying metal, so that's a solid, reacts with oxygen gas, and so that is O2 gas, to produce a white powdery compound, aluminum oxide. All right, so this is when we get to practice our nomenclature. And so aluminum has a common ion charge of 3+. Oxygen has a common ion charge of 2-. This aluminum oxide is following ionic nomenclature rules. So that's an ionic compound. Ionic compounds are always neutral, and so we have to have a chemical formula that's neutral. In order to do that, we can have 2 aluminum ions and 3 oxygen ions. That would give us overall 6 positive charges and overall 6 negative charges, so that it's neutral, electrically neutral. So you have to remember your common ion charges so you can get your chemical formula correct. It says white powdery compound, and so that's implying that it's a solid of some kind because it says powdery. And so now we can balance our equation. I can see that that's a 2 for the oxygen, and then that's a 3 for the oxygen. The lowest common multiple of those is 6, and so I will need to put a 3 there and then a 2 there so that my oxygen counts are, I have 6 oxygens on both sides. And for my aluminums, now I have 2 times 2, which is 4 aluminums, and so I will need a 4 there. Yep. Okay, this will be a separate lecture video. If you want to learn how to classify chemical reactions, watch a different video.